I'm very happy it's being acknowledged. Okay, I'll start by thanking organizers for this wonderful workshop and for the opportunity to speak. In the next 1 hour, I'll try to talk about elliptic generalizations of orthogonal polynomials and the integrable structures. Oh, sorry, 50 minutes. I'm so sorry. I'll try to keep it at 45. Yes, just under 1 hour. Sorry, I'll be talking about elliptic orthogonal polynomials and different integrable structures that are behind these. Okay, and the Simpson is because elliptic. Okay, so I come from the integrable side of the woods. And over the past few years, I've been very interested in elliptic generalizations of different quantities that we know from integrability, mainly Painlevé equations and isomonodromic deformations in general, and also conformal field theories, and that's where I came from into this. Orthogonal polynomials have a very important place in the context of integrable systems. And so with this work, we are combining different lessons I've learned from the elliptic generalizations and applying it to orthogonal polynomials and trying to see what kind of structures are underlying. Please stop me at any point. And I tried to make it non-technical. Anyway, all feedback is much appreciated. I also managed to make the IPAM colors, so just keep an eye out. I tried hard. Anyway, this is a joint work with Tom Latimer and Peter Roffelson, both based at Sydney. Tom is now moving to California, so yeah. Okay, so first, why orthogonal polynomials? Well, they are very useful for many different areas, from random matrices to eigenvalue problems. By that, I just mean Schrodinger equation, for example. And in integrability, these usually appear as very special solutions of highly transcendental equations. So they're very useful when you want to do numerics and understand asymptotics, for example. But they're also very important for random matrices in terms of matrix models and also to understand universality. Since everyone is talking about the 6-vertex model, I went and did some research, and turns out there is this wonderful paper by Filippo, who's here, about the role of orthogonal polynomials in the 6-vertex model, and this will be the only 6-vertex I show in this talk. So if anyone has ideas about how to use any of this technology, I'll be very happy to chat. Okay, so what are orthogonal polynomials? They're a sequence of functions, typically holomorphic, that are defined on a particular support, which is A to B here, and they have a particular weight, W. So in other words, you have a sequence of functions, and you define an inner product. Typically, they have, when you say orthogonal polynomial, you think about a function such that it has a 0 of order n at z equal to 0. Now, I'm talking about monic polynomials, and I'm not considering orthonormality. So these are really orthogonal. Okay, so what are the main ingredients to build up such a polynomial? Of course, again, this is a very biased view because I'm setting everything up because I'm pretty sure a lot of people in this audience are familiar with orthogonal polynomials. I don't need to introduce this, but I'm doing this because then I'm going to show how each of these ingredients generalizes to higher genus. Okay, so the 3 main things that are important in this picture, mainly for generalization, is first the basis. In this case, it is 1zz squared, something easy. For example, then there is the interval, which is A to B, and then there is the weight. There are very well-known examples. For example, Legendre polynomials, the weight is simple, it's 1, and A and B are -1 to 1. Okay, so here we can construct different kinds of polynomials, and there is a very good classification that is well-known for these polynomials. There are 3 main properties I want to focus on. One is the moment representation. I'll show you what that means if you haven't seen it. There is a 3-term recurrence relation, which gives all the polynomials uniquely. And third is the Riemann-Hilbert problem, which I'll also introduce. The moments, so these 3 will be the properties that I also try to reproduce in the elliptic case. Moments are simply defined this way with respect to the weight and zk, which is appearing from here. And the statement is that all the polynomials can be written in terms of moments. So this dn is some normalization factor, so it's just a constant. Don't worry about it too much. So for example, if you look at the determinant, you can expand it as 1 times this whole thing, which should typically be 1 from monic polynomials, or rather, dn is this determinant. And the coefficient of z in the basis expansion will be remove this row, and this is something familiar from understanding the determinant of 3 by 3 matrix. Here we are looking at n by n matrix. It looks complicated, but it's pretty simple. This kind of a description also tells us how to write orthogonal polynomials in terms of Hankel determinants, because this is a Hankel determinant-ish. All orthogonal polynomials also satisfy a 3-term recurrence relation that looks like this. And it's useful to remember this because I'll come back to this, the elliptic generalization of this towards the end. The thing you need to remember is there is zpn, and then you have n plus 1 and n minus 1. Okay, great. Now on to the Riemann-Hilbert problem. This is the technology that was developed in the 1990s by seminal works of Percy Dived, Kricker-Bauer, McLaughlin, the pronunciation might be wrong, and Zhu. I started writing the list of people that have contributed, and I got very overwhelmed really quickly, so I'm not going to do that. But there are several more that have contributed to the development of the Riemann-Hilbert technology for orthogonal polynomials. The main takeaway for the Riemann-Hilbert problem is that you can study, instead of studying the polynomial, you can study such a matrix such that the 1-1 entry gives back the polynomial. Why is this useful? Studying the asymptotics of polynomials in very complicated cases is usually a hard task. But studying the asymptotics of yn is a relatively easier task. So the name of the game is study the asymptotics of yn and try to deduce the asymptotics of the polynomial. That's one of the applications. Oh, that's the Cauchy kernel. So it's a Cauchy transform of the polynomial. So it's going to be I think there is a weight here. Yeah. So that's the Cauchy transform. I will explain how this is a Riemann-Hilbert problem. So typically, the Riemann-Hilbert problem is defined in the following way. You have some contour. In this case, it will be a to b, because that's the interval. Typically, this side is called the plus, and this side is called the minus. And you have something like y plus is y minus times some jump matrix. And in this case, jump is pretty simple. You have 1, the weight, 0, 1. OK. So solving this Riemann-Hilbert problem gives this particular matrix solves this Riemann-Hilbert problem. It has a jump along this interval. And that will be the solution. OK. So there are several other applications to understanding Riemann-Hilbert analysis. One of the most important things is the application to random matrices. This was very instrumental in understanding universality, to obtaining the universality results for random matrices. Oh no. OK. Just to prove my point, I took out a graph from Google Scholar. And you can almost see when the paper was released, which was here. Now, it is only counting articles with the title having orthogonal polynomials, so this is a bit biased. And there is an upward tick towards the end, so that's good. OK, so now what I showed you right now is that the usual orthogonal polynomial story. You have some polynomials. You want to understand what these are. So you're looking at its properties. You have the moments, you have the recursion relation, and most importantly, you have the Riemann-Hilbert problem. Once you have the Riemann-Hilbert problem, you can really unleash quite a lot of structure. So you can understand the integrability, you can understand random matrices, you can understand a whole lot of properties of these polynomials. Now,
what is the vertical axis of this graph? Is it number of particles or no? 0, 0, 0?
Percentage.
Yeah, it's percentage. It's the percentage of articles produced in all articles ever produced.
But is it a lot or not? Like what is the scale? How many papers in seconds? Well,
I can get back to you on that. I don't know.
does the Plato start? Plato read?
Don't read too much into the graph. All I wanted to show was there's a peak. Yeah, we can discuss the graph later. Okay. Now on to the elliptic world. It's a good time to be studying things on the elliptic generalizations. So the point is, the philosophy has been there for a long time, starting from 1970s, and I'll show you the history in a minute. So this has a very rich history of people trying to understand different kind of elliptic functions. Of course, they are not new. But most importantly, in all the other fields, we have seen elliptic generalizations. So for example, to cite my own work, we studied the properties of tau function. And the main takeaway is that when we go to genus 1, we actually find quite a lot of non-trivial properties. We understand topological properties that we can't quite see from genus 0, obviously. But also it gives us very important analytic information about who even is the tau function when you go to genus 1. So not only is it a good problem in itself, but it's giving us more deeper structure of the quantities that we already know. Such one point torus also appeared in yesterday's talk by Jesper. So we can also understand some CFTs there. So the other thing is that you can define some sort of a master class of equations. One of these examples is Landau-Lifshitz equation, which gives NLS and several other integrable PDEs as specific limits. So studying elliptic generalizations might actually give you a more general class of equations, more general class of integrability, and give you very important properties. There are many such elliptic generalizations that we've seen, not necessarily in the polynomial world, but elsewhere. For example, in Borodin's talk, and there are some, maybe I misspelled his name, but okay. Okay, so we have orthogonal polynomials. I'm telling you why it's good to see the elliptic cases. Let's now go to the history of orthogonal polynomials in particular. The word elliptic orthogonal polynomial was actually first coined by Ries way back in 1945. What they were observing is that you have some polynomials, in particular generalized Jacobi polynomials, and they observed that these had something to do with elliptic functions. And so they called it elliptic orthogonal polynomials. Since then, there were a lot of work by Karlitz and Jaime between 1945 and 1970, where they started seeing many other functions that had ellipticness in them. In 2000s, there were several important papers with generalizations of Chebyshev polynomials and Akiezer polynomials. And I also want to mention the works of Frank Niehoff, who did something actually not too far away from what I'm going to show in the sense of the moments, especially. So the ideas were there. What was lacking was techniques. So we wanted to understand, so the main hard part is how do we generalize, especially the Riemann-Hilbert technique, to go into the genus 1 realm. Okay, so in 2005 to 15, there were again papers by S.L. Bazer and others, where for the first time they showed the relation between all these generalized Jacobi polynomials and Painlevé equations for the first time. In particular, the main message is that these generalized Jacobi polynomials solve the elliptic form of Painlevé 6 equation. And such an equation actually was known to Painlevé himself. You take the usual ODE on the complex plane. You make a change of variable, which is z to y stress p of z. And you get an elliptic equation. And this is called the elliptic form of Painlevé 6, and this is also related to Calogero-Moser models. Okay, so this was the first paper that gave some sort of hint of integrability with these polynomials. Again, they did not use Riemann-Hilbert method. Most importantly, in the recent few years, there were papers by Marco Bertola, Alan Groot, and Arno Kujars on different aspects of elliptic polynomials. And this is where, for the first time, there was some sort of nonlinear steepest descent for polynomials, but it was in a very specific case. There is also a very big difference between the kind of basis that I'm going to consider here and the kind of basis that is featured in Marcos papers. Each of them have their own pros and cons. It depends on what you want to study. You have to choose your basis carefully. So this was our first inspiration to get onto this work. The next one is the papers by Fasondini, Olver, and Shu, between 21 and 23. I know that they're still working on this. They introduced several numerical methods to study what are called bi-orthogonal polynomials. I'll also motivate what the word bi-orthogonality means. And actually, their construction is nearer to ours. But again, the takeaway is that we do Riemann-Hilbert techniques, and we get all the integrability that is behind these polynomials. So the philosophy is not new. The techniques are. OK, so bi-orthogonality very simply means that it's orthogonal not in one variable, but in two variables. OK, so I'm going to show you the following today. First one is construction of these polynomials. So I showed you the three main ingredients that I very carefully chose. So there is the basis, there is the support, and the weight. With this, I'll show you the construction. Then I'll show you the properties. So I'll show you the moment representation. And actually, the recurrence relation can be obtained directly from these polynomials. But I choose to go through Riemann-Hilbert problem. You'll see why. It's much easier. And with the Riemann-Hilbert problem, I now get all the integrability. Throughout this whole procedure, I'll do a sanity check. I'll go back to the even case of polynomials, which means that, for example, in this case, even is just 1 z squared, z to the 4th, and so on. So I'll do the same thing for elliptic case, and I claim that you should go back to the usual case. So I'll show you what exactly it means. But this is a good check to keep in mind, which means that I'm reproducing everything we know and more. I think I want to make another comment, which is that in the previous papers, OK, in these previous papers, mainly these three, what they actually observe is only the even chunk of polynomials. So what they're actually aiming at, or what they're getting by going from something on the complex plane to something on genus 1, is simply 1/2 of the class of functions you can study. Now I'll show you the second half, and always come back to even polynomials to check that I'm on the right path. OK, questions? OK. Let's start with the technicalities. It won't be too technical. I tried, at least. So the first thing you'll observe is that there are no holomorphic functions if you go to higher genus surface. We need meromorphic functions, but we can't have simple poles, because the residue will be 0. So you need at least 2 poles, or a double order pole. So what do we mean? What do we mean by polynomials in this case? We have the following statement. If you have an elliptic curve, in this case it's a cubic. In general, if you have an algebraic curve, is what I want to say. The x and y constitute a suitable basis of functions on that surface. So in the elliptic case, you have a cubic, and this x and y together form a basis, a suitable basis. So here it'll be 1, x, xy, x squared, and so on. So you can consider it, you can consider polynomials as polynomials in x and y as opposed to z. And this is where the word bi-orthogonality comes from also, which is that it's orthogonal both in x and y. Now, the basis itself, so the form of x and y itself, is not, we have some leeway in choosing the basis. For convenience, I want to look at doubly periodic functions. Towards the end, you'll understand why I'm making this choice, but you can do the same with theta functions. You can do the same with other elliptic functions also. The only thing you will need to understand is that depending on where you want your technicalities to be easier and harder, you make this choice. For my case, y stress p is good. What does it look like? Just in case people forgot, it was just a refresher. It has a double pole at z equal to 0. it is doubly periodic, which means z plus 1 is the same as z plus tau. Because it has a double pole, it should have 2 zeros. It is an even function, obviously. And elliptic functions are unique once you specify the pole zeros and, most importantly, the periodicity. Okay, now the derivative, easy. We have a triple pole at z equal to 0. It is, again, a doubly periodic function. And it's an odd function. Okay, let's look at pictures. This is just something you get when you just plot it on Mathematica. All the stars are poles. And since it's doubly periodic, this pole is the same as this pole, same as this pole, same as this pole. These are the 2 zeros that you see. And y stress p function, the p prime function, you'll have a triple pole here, and then 3 zeros. So the 3 zeros are these 3, which are the same as these 2. Okay, so with this, we can construct our basis. I'm chopping up my basis into odd and even, though I don't have to do it. So what are the main properties of my basis? It'll look like, maybe I'll write it there, just because more people are here. My basis will look like 1 near z equal to 0, 1 over z squared, 1 over z cubed, and so on. And this minus 1/2 that you see here is just a normalization factor, so you have monic polynomials. So you have nth order pole for an nth order polynomial in elliptic functions, and this is the basis we are considering. It is doubly periodic, which is nice. Even modes are even, and odd modes are odd. The support we are considering will be this contour gamma. The other normal choice or other canonical choice in this case will be something orthogonal to it, so something like this, but we haven't considered that case. This contour is also something Marco considers in his paper, for example. The main difference between this basis and Marco's basis is simply that I don't have Marco Bertola, sorry. So his basis has 1 over z. It has a simple pole that introduces a whole lot of difficulties that we don't consider, just because it's not natural in this construction. Okay, now onto the weight. Generic weight is too difficult to deal with at the moment. This is a task for the future. But a more manageable case, or the first case whenever you study these, is that you consider n independent weight. We also consider it to be an even weight because that makes our life easy down the road. But several of the results I'm going to show can be extended to any. I think the evenness can be dropped in certain cases. The other thing I want to mention, yeah, tau is imaginary because we want our y stress p to be real on gamma. Okay, so with this, we can construct the polynomial. You have pi m and pi n such that they have nth order pole instead of 0 at z equal to 0. Note, pi 1 doesn't exist, as I just mentioned. A good task for the future is a systematic classification of these polynomials with different weights. We are assuming that weight is strictly positive, time is pure imaginary, as I just mentioned. Okay, so what do the moments look like? You can define moments in much similar way as we do for normal polynomials. I did not write what pi n looks like in terms of mu, just because it looks a bit cumbersome, but it has the exact same structure as the usual polynomials. And they form a checkerboard pattern, which is also true in the usual case. The point to note here is this blue band that is very reminiscent of the Weierstrass sequence of functions, because that's what we are considering. But this also gives us a pictorial intuition of what should happen if you go to higher genus cases. So this blue band keeps increasing in this formalism. Actually, for genus 2, there is as long as you consider hyperelliptic, you can expand this blue band in both sides, and you'll have the same structure. Okay, you can do the same thing with moments, and you can also make some nice plots. You can study the zeros of the moments. This is for n is 2, 3, 4, 5. And you can plot just the polynomials. Now observe that all the zeros of the polynomials will lie on the contour gamma. Okay, so I introduced basis, I constructed elliptic polynomials, I showed you the moments. This also gives a Hanker type determinant for even and odd respectively when it is a mixed case. In other words, if I'm taking the generic pi n, it is not exactly Hankel, but it is almost Hankel. Okay. Now to the main thing, which is the Riemann-Hilbert problem. Much like in the case of this slide, looks almost like what you might expect on the usual complex plane. The only difference you might say is the asymptotic limit, which looks very different. So in other words, in the complex plane, you have z minus n and zn, but now you have a minus 2. I'll explain why that is. Okay, so we can still construct the Riemann-Hilbert problem, which is again going to be on gamma. And you'll have plus minus, and you'll have yn plus, yn minus, and you'll have yn pluses, yn minus jump. Okay, yn is doubly periodic, which means that once you study it on the fundamental domain, you can extend it to the entire doubly periodic lattice. And the weight, again, is the same. It has the same role in the jump function as it does in the genus 0 case. The main difference, the main conceptual difference is that the Cauchy kernel is going to be very, very different. You need to generalize this to genus 1, and that's where your difficulties really begin. Because now you have to prove that this existent is unique, which means that you should have a very good control over the kind of poles that you have inside your Cauchy kernel. And this is where the technical difficulty lies, one of the technical difficulties. So we consider this is the zeta function, which is also related to the y-stress p. Doesn't matter, these are all details. But the most important thing to know is that near in the limit z going to w, the Cauchy kernel always goes as 1 over z minus w, or w minus z. Notably, this Cauchy kernel is not doubly periodic. It actually has non-trivial periodicities. But because of the way that we chose our basis, that non-trivialities are cancelled inside the Riemann-Hilbert problem. And in the end, the matrix that we are seeing here is actually doubly periodic. So we retain that property. The other very important thing is that the determinant is not a constant. So this is what happens. This is reminiscent of genus 1. Not only is it not a constant, you have a y-stress p in there. Now, good thing, it is doubly periodic. So we have the most important property that we want to preserve. Bad thing, it is z-dependent, which means that it makes our life very complicated to really understand the uniqueness of this Riemann-Hilbert, the solution to the Riemann-Hilbert problem. Completely omitting technical details, you can indeed prove that this exists and is unique. And now we are off to the races. Oh, another thing, the C2n and C2n minus 1, these are just the first basis expansion. These are just the constants that come in the basis expansion of the pi n. And they're just coming from this element and this element. Anyway, that's the technicality. But it is y-stress p plus some constant. That's the most important thing with the determinant. OK, sanity check. What happens when you only, because the weight function is even, your polynomials immediately split into odd and even. This is also something you can see just from here. All the mixed derivatives, mixed moments are 0, which means that you have a very nice splitting of your polynomials into odd and even. OK, so look at only the even case. The basis will just be 1, p squared, and so on. Make a change of variable, you get the usual basis. This should be a capital P, I'm sorry. And if you just consider weight equal to 1, you get the modified Jacobi weight. So there are two main takeaways here. One is that this is going back to what we already know in the literature. Second thing is that it's much easier to study this than this. So all the results we are getting from here, it takes a lot of technical analysis. But instead, if you go into the elliptic case, the weight is simply 1. And that's a much simpler case to study. And we can indeed reproduce several of the results just by going to genus 1. So this is yet another my pitch to encourage everyone to go into genus 1. Okay, so this is what exactly I mean by going into the even.
Here, ABC are the EI of the elliptic curve?
Yeah, almost, yeah. Okay, so now we've reproduced, at least from the moments part, we have everything that we need to know. We've made the sanity check. And I will move on to the Riemann-Hilbert problem. Okay, so as I said, the recurrence relation can be just defined, but I'll go through Riemann-Hilbert analysis. The first result is that we have this yn, which is, maybe I should write it down. Is this visible? Okay. So just to have it in the back of your mind, this is what yn looks like. So now, if you shift n to n plus 1, you see that it indeed solves a linear difference equation. And this is the whole name of the game. So Riemann-Hilbert is very important. Why? Because it takes something nonlinear and makes it linear. So here we have a very nice linear equation, although it is 2 by 2. Okay, how do I get this equation? Look at this quantity. So take this, shift it by n plus 1, take yn inverse, and determinant yn. Why is this important? Because this determinant yn is again z-dependent, so we need to keep track of a lot of things. Second thing, look at the asymptotic behavior of yn. So pi n typically goes as z to the minus n. This goes as z to the minus n plus 1. So look at the asymptotic behavior. This automatically gives you what the order of pole on genus 1 should be. The zeros will stay the same because everything is doubly periodic and we made the basis exactly to match this. The last thing is that everything is doubly periodic. As I said, that was our most important property. So if you put all these three together, you can uniquely determine what this Rn should look like because you have unique properties for elliptic functions. So the most technical small subtlety is that this is the only part that we need to get through these three. So in other words, Fn is just a determinant. You get it for free by just looking at this quantity. I'm just going through the sketch because this is what will be repeated for the next 20 or so minutes. Less than 20 minutes, I'm sorry. And so you're left with just understanding what 1, 1 looks like, and you can see that it goes as 1 over z cubed, and that is p prime, because we have double periodicity. Okay, great. We have Rn. Now, the three-term recurrence relation is almost immediate, because you have yn plus 1. So you have pi n plus 1 here, which is yn plus 1. Whatever this is some matrix that I wrote here times yn. So you'll immediately get that pi n plus 1 is this plus this. So that's a three-term recurrence relation, and this is how we get recurrence relations from Riemann-Hilbert problems. Okay, so this looks a bit complicated, but again, sanity check. Go to the even case. It gives back exactly what we know from genus 0 case. So this is the recurrence relation for mixed polynomials. This is the recurrence relation for even polynomials. Now, you can also get recurrence relations for this beta n explicitly, though much like what we have in genus 0 case. I'm not going to show you that because it will fill up my slide. We are yet to find a much nicer description of the recursion relation for the coefficients of this equation. Okay? Now, what about integrability? You take the differential equation instead. You have the Lax matrix. As I said before, the most important thing again is the proof is much like here. Instead of yn plus 1, you have yn prime. So with yn prime in mind, you can obtain this equation. And again, the only non-constant, non-determinant parts are 1, 1, and 2, 2. Looking at the asymptotics and looking at double periodicity, you can fix them to be these functions. The other upshot is that this immediately gives us a second-order differential equation for elliptic orthogonal polynomials, and that comes just by solving that equation. So you'll have pi n prime, that gives the first derivative, and whatever comes next gives the second derivative. So you'll get two sets of equations, you solve them, you get a second-order differential equation for your elliptic polynomials. The other thing I wanted to mention is that all of this can be done for doubly periodic weight. This can be done only for constant weight. So we are still trying to understand how to generalize this for any arbitrary weight, and this is a bit of a challenge. The sanity check in the case of integrability is actually quite interesting. When did I start 15? How much time do I have? Like 10 minutes. Okay, great. Thanks. Okay. Sorry. The sanity check for this case is actually very interesting. Let us restrict this to just the even case. So you have y to n is L to n, y to n. And then you can take the modular parameter of the torus to be the time of Painlevé. You can do the same trick. You can study the differential equation with respect to tau. And this gives the second equation. These two together are immediately the Lax pair of Painlevé 6 equation, the elliptic form of Painlevé 6. And even more interestingly, these give the Hitchin case. Hitchin case corresponds to very specific choice of parameters that have many other applications also that I may not go into. So with these two equations, you can actually get the elliptic Painlevé 6. So this is elliptic. And if you want to get to the usual one, you make the change of variables. You take your y stress p of z to z. And most importantly, there is some other variable. The modular parameter actually goes into the Painlevé time. This is actually a very nice computation to do. So this gives almost entirely the full details of what we want with Painlevé equations. The other thing we get from here is that we had Hankel determinants, or we have Hankel determinants in the case of even polynomials. With the moments and with all of this, we can actually write the tau function of the elliptic form of Painlevé 6 in terms of the Hankel determinants of elliptic polynomials. Now, this is not a new result, but it is a sanity check. This was also the result, almost, that was obtained in the paper by Estelle. Okay, finally, we can actually do something a bit more, which is the compatibility condition and the differential difference equation. This, in the case of genus 0, is just going to give me some sort of discrete Painlevé equation, additive discrete Painlevé equation. And the way you're getting this is just by saying that yn. Sorry, I just wanted to show that just in case you've never seen this in this crowd. So you want to say that, yeah. This looks like a very silly equation from this point of view, but essentially what I'm trying to say is that if you have Rn yn prime, this is the same as ln yn n plus 1. I hope that's clear. Then you get Rn prime minus ln plus 1 plus Rn ln Rn plus 1. By the way, this is the same kind of compatibility that gives you Painlevé in the even case that I was showing you before. Now, this looks a bit complicated. But the point is that we are almost sure that there should be some very specific structure in these equations, because in the even case, this almost looks like discrete Painlevé, although we still have to figure out exactly. We haven't proven this, or we haven't really given any statement, but we know intuitively that this should give some discrete Painlevé. I have also been told yesterday about this incredible word by Dima. Terrible means it's great, and it's horrible. So depending on who you ask, these equations might be great or awful. It's great because you can actually do numerics. You can actually compute these functions. You can know everything you need to know about it. Oh, G2 and G3 here are actually very nice because these are modular functions. So you have these coefficients that can be determined in terms of modular functions, which is just screaming very good geometry. But it's very hard to see what exactly these equations mean, and that is something that we are trying to understand. Sanity check. You go to the even polynomials, and this should give back the equations that we are well familiar with. OK, I'll get to my conclusion. What I showed you today is I did a setup of what we know about orthogonal polynomials on the plane. Then we went onto the torus. With systematic study of Riemann-Hilbert problem, I showed you all the properties that we can get. Specifically, we can construct the polynomials. We know its moments. We know its Hankel determinant type structures. We can get the Riemann-Hilbert problem. With it, you can get quite a lot of integrable structures. Now, the point is that I'm also working on nonlinear steepest descent analysis for these kind of cases. So I'm fairly confident that generic weight might not be too hard in a couple of years. So with this, you have integrability, and you have all the nice structures that you want. Now, there are many open problems. An immediate thing is asymptotic analysis of these polynomials. So do nonlinear steepest descent. Try to understand what it looks like. A systematic classification. Oh, sorry, classification. There is a typo. With more complicated weights. And this I expect it to be something similar to, oh, you have the elliptic generalization of Laguerre polynomials, elliptic generalization of some other type of polynomials. Oh, sorry, there are so many typos. There is higher genus extensions. Sorry. So as I showed you before, the main thing with higher genus is the philosophy again is there, but the technicalities are the main problem. So you have this x and y. You can use the same kind of basis with x and y now having higher order poles. And what I expect, if you've seen the Weierstrass sequences for genus 2 curves and so on, you can almost guess what I'm going to do next. So the first two things will be missing in the hyperelliptic case. For more general genus 2, I don't even know where to start. But if you restrict it to hyperelliptic case, then there are several hints about how to generalize almost everything, and it'll be very interesting to see what kind of integrable structures are underlying them. The next thing is application to random matrices. Are there ensembles of these polynomials, and how do we understand it? What does it mean? We can also get some possible universality results. It's just a teaser. Something might be in the works. I don't want to talk too much about it. But it's not too hard to expect what I'm going to be talking about here. So the point is that you can understand Christoffel-Darboux type construction for polynomials and try to understand what this gives in the limits. And this should automatically give something like the signed kernels and airy kernels, and possibly some non-trivial generalizations in genus 1 case. So yeah, I think I'll stop now. I was 5 minutes early.
Thank you.